Hey everyone. So next up in our conversation is radical functions. A radical function exists in the form y equals a square root of b x minus h plus k. Now the a, the b, the h, and the k are the a, the b, the h, and the k that you've come to know and love. So all of that should feel familiar to you from the transformation stuff that we've already talked about. We do need to think about restrictions with radical graphs. The radicand must always be greater than 0. So don't get caught in thinking that that means x has to be greater than 0. The whole thing underneath has to be greater than 0. And that's because I can't take the square root of a negative number. These graphs have a distinct starting point, and that would be at hk, because originally, if we look at the base function of y equals the root of x, that started at 0, 0. Okay, so if I then move horizontally h units right or left and k units up or down, my new starting point is going to be at h comma k. Okay, when building equations, the value for a can be written as a value for b and vice versa. So just a little quick conversation around that. If I told you your base function was y equals the root of x, and then I said, okay, let's take a look at y equals 3 root x. You would tell me that that is taking y equals the root of x and performing a vertical stretch by a factor of a third on it, or sorry, vertical stretch by a factor of 3 on it, okay? Vertical stretch by a factor of 3. But if I did this, you would tell me, well, that's taking this guy and doing a horizontal stretch by a factor of 1/9. But what I need you to see is these are actually the same graph, okay? Because the square root of 9 is 3. So mathematically, there's no difference between these two guys, okay? So A and B, when we're doing radical graphs, can be kind of interchangeable. So either we'll force you to use a particular letter, and you'll notice that in the question, or we'd have to accept both answers. Okay, solving equations in 30-1 is usually done with technology, but we will review the algebra just to make sure you are cool with that. So question 1, the graph of f of x equals the root of x has been transformed to become g of x equals 2 root of negative x plus 3 minus 5. Just a quick little reminder, make sure this guy here is in factored form. It already is, so that's awesome, but just something to double check, okay? Describe the transformations and draw a sketch of the graph below. Okay, so let's start with domain. In order to figure out domain, I just essentially take my radicand and I set it equal to 0. So I'm going to say, okay, negative x plus 3 has to be greater than or equal to 0, which means x plus 3 has to be less than or equal to 0. I divided both sides by -1. When you divide by a negative, your inequality will flip. Okay, and that kind of makes sense if you think about the fact that I started like this and I'm doing a horizontal reflection there, right? So if I'm doing a horizontal reflection, the greater than 0 portion is going to become less than 0 because it's going to go this way. Okay, and then I'd have x is less than or equal to -3. Okay, so my domain would be all the members of the real such that x is less than or equal to -3. The range, well, the original one would have been y is greater than 0. I've moved that down 5, so now I'm going to be greater than -5. Okay. So -∞ to -3 and -5 to infinity. Transformations, there's 1, 2, 3, 4 things you need to say. You'd want to start with your vertical stretch of 2 about the x-axis. Then you'd want to move to your horizontal reflection about the y-axis. Then your horizontal translation 3 left, because your h value there is -3, and a vertical translation 5 down. Okay, and then this is the graph. The blue graph here is the root of x, and then the red graph is the result of the new function. So it's 2 root of negative x plus 3 minus 5. You can see that I have flipped it horizontally. I've moved it 3 to the left, 5 down, and there's also a stretch there. So it's growing, it's kind of growing quicker there. Okay, awesome. Build an equation for the following graph, knowing that it passes through the point 3, -2. So any sort of equation we build, we want to think about, do I want an a value or do I want a b value here? For sure, I have vertically reflected this just based on the orientation, and I have not horizontally reflected this. So I'm actually going to build this with an A because I know that my A value is going to have to turn out to be negative anyway. Okay, I know that my starting point is 2 comma negative 1. So my H is 2 and my K is 1. Then the friendly point I was given was 3 comma negative 2. So I'll plug negative 2 in for Y and 3 in for X, and that's going to allow me to solve for K. So 3 minus 2 is 1. The square root of 1 is 1. So that's A plus 1, and then I subtracted 1 from both sides. That gave me A equals negative 3. And then be careful, you weren't asked to solve for A, you were asked to actually get the equation. So the equation itself is Y equals negative 3 root of X minus 2 plus 1. Now, if you had wanted to write that as a B value, you could. 3 could have been a 9 on the inside, but you'd have to leave the negative on the outside because the negative on the outside is your vertical reflection. If you tried to bring that negative in, you're actually switching it to a horizontal reflection, and you don't want to do that. Okay? All right, state the domain and range of Y equals P root of negative QX minus S plus T. Now, the very first thing I want you to notice here is this negative Q has to be factored out. Okay, you can't read transformations unless you're in fully factored form. So I'm going to rewrite this, first of all, in that factored form. So negative Q will come out, and that will leave me with X plus S over Q. Okay, so now that I've written it in factored form, I'm ready to state my transformations. Oh, sorry, no, not transformations. I'm ready to state the domain and range. So the domain comes from the restrictions on the inside, right? So I could go back to here if I wanted and just say negative QX minus S has to be greater than 0. So if I did that, I'd go negative QX minus S has to be greater than or equal to 0. Negative QX has to be greater than or equal to S. I just add S to both sides. Divide both sides by negative Q. S is less than, again, remember, when I divide by negative, I have to flip the inequality. X is less than negative S over Q. Okay. So essentially, I'd go from negative, if you want to write it in interval notation, I'd go from negative infinity to negative S over Q. Or I could say X is less than negative X over Q. The range, I'm starting at 0, 0. I'm going to multiply everything by P. That won't affect the range. But then I'm going to go up T units. So now it's going to be greater than T instead of greater than 0. Okay? Good job. Okay, oh, let me take that ink off for you. The graph of Y equals the root of X is transformed to Y equals A root X, a transformation on the original graph that would have resulted in the same graph as Y equals A root X. Well, what are we trying to get at there? We're trying to get at the fact that Y equals A root X is the same as what? If I wanted this underneath the square root, what would I be at? I would be at Y equals the root of A squared X. Okay, the root of A squared X is the same as saying A root X. So this was a vertical stretch of A. What's this now? It's a horizontal stretch, and it's a horizontal stretch of 1 over A squared. Okay, 1 over A squared. So your answer there would be B. Okay. All right, solve the following algebraically. When we go to solve algebraically, we want to get the radicand all by itself so that we can square both sides. So I'm going to add 3 to both sides, and then I'm going to square. Remember, that's x plus 3 all squared. That's a binomial squared. So you square the first, double the product, square the last. Then the root of x plus 5 squared will give me just x plus 5. Now I've got a quadratic here. In order to solve the quadratic, I want to bring everything over to one side so that it equals 0. And then I'll try and factor it. So I minus x from both sides. I minus 5 from both sides. Two numbers that multiply together to give me a 4, add together to give me a 5 would be 1 and 4. Therefore, x is -1 and -4. Now, with radicals, if you're solving algebraically, you do need to check them. You need to verify that they actually work. And the reason is because they could be extraneous. They may not actually work in the equation. So here we go to check them. I'm using the -1 first. So everywhere where I saw x, I'm plugging it in with -1. That gives me -1 equals -1. So that's cool. Okay. Just for clarification, -1 plus 5 is 4. Root of 4 is 2. 2 minus 3 is -1. Okay. Check the other guy. This would give me the root of 1. 1 minus 3 is -2. So that one doesn't work. That guy's extraneous. And my only solution there would be x equals -1. Okay. Okay, now graphically, solve the following graphically, round your solutions to the nearest hundredth. Okay, so all we're doing here is you're going to stick this in y1, this in y2. The picture you should get should look like this after you have already paused me and done it yourself, of course. The picture you get should look like this. And then we see there's only one solution here, and that solution is -2.33 when rounded to the nearest hundredth. Okay. Okay, a square root function can be described by y equals the root of f of x. Essentially, you're taking the square root of all the y values of your original function, okay? So the point, for instance, the point 416 would become the point 4, okay? What I want you to notice there is I did not touch x. X stays exactly the same. Lots of kids tell me that the point 416 becomes the point 24 because they get all excited that both of these are perfect squares. It doesn't matter. X stays the same. You're only square rooting y, okay? Your invariant points will exist at y equals 0 and y equals 1, and that's because the square root of 0 is 0 and the square root of 1 is 1. Okay, so those guys won't be altered at all. Now, when I do that, I separate into 3 distinct regions, okay? So say I just had, for an example, a line that looks like this, and then I saw that I had an invariant point at 0 and at 1. So there and there we'll say is 0 and 1. So what I want you to notice is I'm splitting this up. These are not asymptotes. I'm just showing you the region there, but I'm splitting this up into 3 different regions. 1, where y is less than 0. 1, where y is in between 0 and 1. And 1, where y is greater than 1. Okay? And the same thing is always happening within these 3 regions. In the y is less than 0 region, when y was negative, nothing exists in my square root graph because I can't take the square root of a negative number. So for instance, all of this stuff here from the original function is not going to create a square root graph because you can't take the square root of a negative number. When y is in between 0 and 1, y is a fraction. The square root of a fraction is always actually bigger than the original number. The square root of a quarter is a half. A half is bigger than a quarter. So what happens there is you are always, the square root graph is always above the original function there, okay? So you want to make sure your line actually goes above. Then when y is when y is greater than 1, the square root of any number greater than 1 will be less than the original number. And so from here on in, I'll be on the bottom, I'll be underneath the graph, and I'll look something like that. Okay, and you guys are going to practice drawing these in your book in just a couple minutes here. If you're lost and you do have an original equation, you can type the original equation into y1, and then in y2, just write the square root of y1, okay? All right, so we're going to draw a sketch of each of the square root graphs, and then we're going to state the domain and range. Okay, so for this guy, this is going to be very similar to what I did here. You're going to set yourself up that you find your invariant points, which are y equals 0 and y equals 1. You also want to find your other friendly points. Your other friendly points is go to y equals 4, and where the graph exists at y equals 4, you can drop that down to 2 because the square root of 4 is 2. And then if you happen to have it, go to y equals 9, because you know the square root of 9 is 3, okay? So when you do that, you should end up with a graph that looks like this. So I just want to make the point. I had invariant points at 0, make the point. And then I had invariant points at 1. And then at 4, 1, 2, 3, 4, I dropped down to 2. And at 9, I dropped down to 3, okay? All right, now the domain and the range. The domain will be greater than whatever that point there was. Okay, it looks like it was -2. And then my range will be greater than 0 because I start at 0 and I head up. Okay, awesome. Let's try the next guy. So now, again, I'm going to plot at 0. I'm going to plot at 1. Those will be invariant points. At 1, 2, 3, 4, I'll drop down to 2. And at 9, I'll drop down to 3. So I should end up looking, I'm going to try this with a mouse. Okay, I should end up looking like that. Just make sure in here that you are above the original function, okay? Okay, and so here's the computer generated graph. Not bad if I do say so myself. The domain of that will be less than 1, 2, 3, 4. So x is less than 4 and y is greater than 0. Okay, less than or equal to 4. Sorry, I was getting lazy in my conversation there. Don't be lazy. I want you to make 100 on your diploma. Okay. All right, this guy. How many invariant points will I have? First of all, the correct answer to that was 4. I'm hoping that's what you said to me. I will have 1, 2, 3, 4 invariant points there. Okay. Also find where y equals 4, drop it down to 2. Find where y equals 9, drop it down to 3 because you know those square roots. Nothing exists in here. So this actually ends up being what we call a two-tailed graph. You'll have kind of 2 tails going in opposite directions there. Okay, so it'll look something like that. Domain, we've got what? 1, 2, 3. So x is less than or equal to -3, and x is greater than or equal to 1. And then x is the number of the reals. If you wanted to do that in interval notation, you'd go -infinity to -3 in union with -1 to infinity. Okay, and then the range again will be greater than 0 for this guy. Okay. All right, we're going to try a opening down quadratic. Let me take those ink things off for you. Again, we have 4 invariant points. We've got 0 and we've got 1. The other thing is you're going to want this guy to be decent. That happens to be at 9, so that's super friendly to us. I know I'm going to drop that down to 3. 1, 2, 3, so it'll be like right there. And then I can connect those. Okay, so it should look something like this. Domain of that is going to be, what's that? -1, 2, 3, 4, 5, 6, 7. So -7 to -1. And my range will be from 0 to 3. Okay, it's not to infinity anymore because there's an actual top to this guy. So y will be 0 to 3. Okay. Okay, try this guy. Draw a sketch. So things I want you to notice, this straight line here is going to have to be a straight line. Okay, and that's at 1, 2, 3, 4. So I'm going to have a straight line at 2. So I'm going to be like that. Okay, then I know that I have invariant points at 0 and at 1. So I'm going to curve myself up to there. And then over here, I have invariant points at 0 and at 1. I can know 4 will drop down to 2. And so I'd be looking at something like that. Okay, I'm going to put arrowheads on both sides because this does spill off the page. In a computer-generated drawing, you don't need the arrowheads, but in a hand drawing, you do need the arrowheads. Okay. Okay, so the domain is less than -2 and greater than 4. And then my range will actually be y is greater than 0 here because although that guy caps at 2, this guy over here keeps going up forever. Okay, and because he keeps going up forever, y is just greater than 0. Okay, awesome. Okay, draw a sketch of this guy then. Again, just finding your friendly points. 1 is going to stay at 1, 0 is going to stay at 0, 4 will drop down to 2, 9 will drop down to 3. You should get something that looks like that. This guy stopped, so you have to stop. There'd be no arrowheads here because you actually did stop. Okay. So my domain is from -6 to, what's that? 1, 2, 3, 4, 5, 6, 7, 8. -6 to 8. And then my range, I don't go any higher than that point, right? So that would be 0 to 3. Okay. Make sure your domain and range is very exact. If you're writing in set notation, if you don't have all the values of x such that, they'll take half a point off. If you don't have x as a member of the reals at the end of it, they'll take half a point off. If you don't have it set up like this, where it goes smaller is less than or equal to letter is less than or equal to larger, if you write that backwards and with greater than signs, they'll mark it wrong. Okay, so you have to be super, super careful with how you're writing domain and range. Okay, if the range of y equals f of x is y such that -16 is less than or equal to y is less than or equal to 144, and y is a member of the reals, then the range of y equals f of x can be written as a to b. What's the value of a plus b? So there are 3 common answers I get here. They are 8, 12, and 16. I bet you have one of those answers, 8, 12, and 16. The correct answer is 12, but I wanted to show you why. So this range of the original graph starts in the negatives. Well, you can't take the square root of a negative number. So your range can only start at 0, okay? So your a value here is actually 0, and then your b value will be the root of 144, and the root of 144 is 12, okay? So 0 plus 12 is 12. Okay? Awesome. Okay, so that's it for radicals, and that's also it for part 1 of our time together. So next up, we'll start part 2 with rationals. Okay, see you soon.